Welcome to our first elliptic geometry video. Let's meet the easiest way to make elliptic lines. We're going to look at all the different kinds of elliptic lines that we can make. Remember, elliptic lines go through antipodal points. So a point at 12 o'clock and at 6 o'clock. These two antipodal, 12, or these two antipodal. So I can literally, with crosshairs drawn in, if you got a pair of perpendicular axes drawn in going through O, you can put the point of your compass anywhere on one of these two sides. Put the point of the compass anywhere. Extend the compass to hit that antipodal point and its cousin. So these 2 points that are across from each other, and make an elliptic line. Isn't that great? All you need to do is have crosshairs, and you can make elliptic lines all day. Let's do another one. Suppose I choose a point outside the circle. So I've got this point out here. I'm using that as my center, picked out of thin air. Well, I got to go through the 2 points that are at opposite ends of a diameter from that point of view of that point that I took as center. So here's another elliptic line. So there's 2 elliptic lines. Now, it's also the case that diameters are also elliptic lines. So after these 2 brief moves, we already have in our picture an elliptic quadrilateral called OABC. So there's this elliptic quadrilateral. Let me turn it this way so it looks good on your camera there. And let's look at the properties of it. Well, I know that's 90 degrees, the angle at O. Since this center was on this Euclidean diameter, that means that's a 90-degree angle. So I've got a 90-degree angle there. And for the same reason, this center here was on that diameter, so that gives me a 90-degree angle here. And this was already 90, like I said. So now we've got a quadrilateral with 3 90-degree angles, and that 4th angle, check it out. Do you see how it's fatter than 90? And in hyperbolic, that angle was pinched to be less than 90. This time, the sum of the angles of elliptic polygons always adds up to more than the Euclidean size. So for a triangle, the 3 angles have to add up to more than 180. For a quadrilateral, the 4 angles have to add up to more than 360. Those are really easy elliptic lines to make. Another thing is we would measure this angle at B by the usual way. We're going to measure them with tangents. So if I had to figure out the measure of angle B, I'd have to find this tangent. Constructing it's just good. So I've got that tangent. And then I have to come over to that other center, draw that radius in, do its tangent, and the angle between these 2 tangent lines, this much, let me mark it in, that much there, that would be the angle formed by the red elliptic lines. And you can see it's much more than 90. You can see it's way more than 90, which we predicted. Now, if you need to get the exact measure, well, then you're going to need to know something about the geometry, the Euclidean geometry of the straight pieces, and get some triangles, some other kind of measurements, something, because you can't just say, well, I've got 4 angles, they have to add up to a certain amount. They don't have to add up to a certain amount except for more than 360. All right, let's see some more elliptic lines. Now, I've got the crosshairs again, so that allows me to make, in a sense, the easiest elliptic lines of all time. Use this point. See how that point right there? It's at the end of a diameter, and I set up my compass to catch the antipodal points at the other end. So it's like I draw crosshairs and don't draw anything else. So there's a really nice elliptic line. I'll do the other one at the other end. I don't have to change the size of my compass. Come over here, put that down, see? I'm going to make this pair. So this gives me the following. I get a thing called a loon, this eyeball shape, that's a loon. And check it out. Since I already know that each of these 4 radii are the same size, that means that if I were to draw the tangents at the point of intersection at that point there. If I were to draw that tangent, it would have to catch this other center because of the isosceles right triangle that is forming the stuff. I have these two tangents meeting at a 90-degree angle. So this thing here, this red eyeball, is a 90-degree lune. 90-degree lune. And it cost me nothing. I did almost no work, and I've got this beautiful lune. And what's interesting about this lune is it is a two-sided polygon with all right angles. So that's in this red shape here. That's the 90-degree lune. In the same picture, without doing any more work, I also have, if you consider this thing, or let's name that 90-degree lune. I'll give it a name here. I'm going to call this point A, this point B, and let's call this C and this D. You could call this 90-degree lune A, D, B, C if you wanted to. I'm naming it with 4 letters just to make sure other people know what I'm talking about. I'm naming it with 4 letters even though it's only got 2 sides. Another thing that's funny about what's going on is I named A and B as if they were different points. They are different Euclidean points, but A and B are the same elliptic point. These 2 points are treated the same in elliptic geometry. So I have 2 elliptic lines through 1 point that somehow close up and make an enclosed area, a very strange animal. I also have right angles here, as we saw in the previous piece of paper, which means I have a triangle in this picture. Triangle ACD is all right angles. So that's kind of interesting, just because if you remember what happened in hyperbolic, we had all right angles for 5 sides, 6 sides, 7 sides, 8 sides, any size, number of sides more than 5, we could have all right angles. In Euclidean, the only way to have all right angles is 4 sides. And this one completes the story, 2 sides or 3 sides, all right angles. And this picture has examples of both. So that's kind of sweet. Now the last thing is the big idea. Suppose somebody just gives you 2 points. You don't have any crosshairs, you don't have any shortcuts. Suppose I need to get the elliptic line through any 2 points given. So here's this construction. It's in the book. The proof for why this construction works is in the book. But you're going to need this construction if you ever need to make a line through any 2 points. So step 1, you get your compass to be the size from O to A. And you get the reflection of, hang on, let me get that right on there. Let me get that right on. Okay. You reflect the point A across the circle O. So there's an arc on the other side of the world. And I am going to make the ray OA, but I'm going to extend it away from O. Or sorry, away from A. All the way over there. And now what I have to do is, I'm going to call this point, and this is what I do in the book, I'm going to call that point Z. Because I reflected A across O. So it's like I'm reflecting it across the alphabet. Now I have to construct the inverse of Z. When I construct the inverse of Z, I will have an important point. I will have a point that has to be on any elliptic line that goes through A. So I'm doing the same old moves that we have done so many times. I'm constructing the regular old inverse of point Z across circle O. So these steps, I hope, look extremely familiar. And if they don't, well, you better brush up because we'll be using these moves a lot. So this point that I just constructed way over here, let's get it in the picture, that point is Z inverse. And here's the truth. This is proved in the book. Any elliptic line through A must contain Z inverse. So now I have 2 points that have to lie on the circle that I seek. So what I'm going to do is this. I'm going to get the perpendicular bisector of A Z inverse, and I'm going to have it intersect the perpendicular bisector of AB. And where those perpendicular bisectors intersect will be the place that will be the center of my elliptic line through A and B. So I've got a little bit of constructing to do. I'm going to get the perpendicular bisector of AZ first. So here we go. I've got A and Z in the picture. So I make my compass more than halfway from A to Z inverse. And that's easily more than halfway. So I make a big arc up here and an arc down here. I put the point of my compass at Z inverse. And I do the same thing. I caught it, and I caught it. So I've got those two nice red X's. I'm going to join them. And I really don't need to draw the whole thing, but it's only because I know approximately where the perpendicular bisector of AB is going to go. Perpendicular bisector of AB is going to catch in here. But I'll draw the whole thing because, well, we may as well just draw it. So there's the perpendicular bisector of AZ inverse. It's getting kind of close to Z. That was just coincidence. Don't worry about it. So that's the perpendicular bisector of AZ inverse. Now all I'm going to do is the perpendicular bisector of AB. So I'm going to draw that segment AB, which technically I don't have to do, but we may as well see what we're doing the perpendicular bisector of. I'm going to make a little X above and below this segment, this small segment. And keep my marks kind of tight together here. And there's my perpendicular bisector. And where these two perpendicular bisectors intersect is the desired center of the circle that is going to not only go through, so right there, that point, that's the center of the circle that's going to go through AB, and it's guaranteed to go through antipodal points. Well, let's see if I'm right. So I put the point of my compass there. I catch A. Let me get my big fat hand out of the way there. See, I caught point A. Now I'm going to try and catch, I'm going to make sure it catches point B. Catches A, catches B. Oh, that's a good sign. I'm catching point A and point B. Now I'm going to draw this circle. It's going through A and B. And that should be an elliptic line. Now what makes that an elliptic line? Well, it's supposed to go through antipodal points. So let's lay down that ruler and catch these two antipodal points. Let's catch them. Now when I draw that in, I had better cross the point O. So let's get this going here. I'm going to go like so. And I miss point O by a millimeter. I miss it by a little bit. Well, that's what I get for hand drawing. But that's pretty close. These steps are, so when you do it in Sketchpad, it's perfect every time. That diameter will catch O right on the money. But anyway, this is an elliptic line because it's the arc of a circle that goes through antipodal points. And I started with 2 points. So 2 points determine a line. And that's our show. What did we learn today? We learned some easy elliptic lines. We learned about 90-degree lunes and 90-degree triangles. And we learned measuring elliptic lines using tangents. So go ahead, get on that wiki and answer a bunch of questions.